All right, well, let me also thank the organizers for putting together this magnificent meeting. I've really learned a lot, and there's a lot for me to think about over the next few weeks. We were told that we could be unconventional, so I'm going to start out being unconventional by asking you to go back 80 years and pretending that the Klein-Gordon equation actually worked. What I mean when I say that it worked is that it worked as a single particle theory. So what this is in effect is maybe what the Klein-Gordon equation should have been. It seems to be a viable relativistic quantum theory of single particles. So that's taking us back 80 years or so. At the same time, it is not actually equivalent to the Klein-Gordon, mathematically speaking, nor to the Schrödinger equation. So it's something different that actually, in principle, gives you predictions that you could verify experimentally if you wanted to. So how is it that we do this? We do this by doing something else that's quite unconventional. We throw away the wave function altogether. There's been a lot of talk about what the wave function is, whether it has ontic or epistemological meaning and this kind of thing. This, I think, adds a whole new wrinkle in that we're suggesting that the wave function may not exist. Now, I'm not actually willing yet to claim that it's dead. I rather think of it in a superposition state. It could be dead, it could be alive. We don't really know. But certainly we can say that mathematically it's completely extraneous. It's absolutely unnecessary. And the latest wrinkle in this work, which is today's talk on the relativistic generalization, so far as I know, there's no way actually to make that work with a wave function, certainly not with a linear wave equation. You really have to use a different approach that is inherently nonlinear. Which is the approach that I talk about. But in the non-relativistic limit, it does reduce to something that is mathematically equivalent to the time-dependent Schrödinger equation. So if we don't have a wave function, what do we have? Well, we have ensembles of trajectories. So in a sort of 1 + 1 space, psi of x is replaced with an ensemble of trajectories. And we have, of course, x of t, but then we need an additional coordinate c, which we call the trajectory labeling coordinate, to label a specific or individual trajectory within our ensemble. And these things foliate the space-time, that is to say, there's one trajectory, exactly one passing through every point in space and time. They don't intersect with each other, and this then is the fundamental object that we try to obtain through some kind of dynamical partial differential equation. It's a little bit weird. I'm going to talk about spatial derivatives, but remember, x is the dependent variable now. C is the independent variable. So when I say spatial derivative, most of the time I'm talking about a derivative with respect to C. Now, the curious thing, you can go through and do this, and our derivation, by the way, we don't start with the Schrödinger equation. We start with more fundamental principles. I'm now talking about the non-relativistic case. And in the non-relativistic case, you find that our trajectories are exactly the trajectories of David Bohm. One of the things that's been interesting to me about this meeting is to see all the different contexts in which Bohmian trajectories seem to arise. Whether you sort of buy into David Bohm philosophically or not is another story. And in fact, I want to make it very clear from the start that this is not Bohmian mechanics by any means. To start with, David Bohm has the advantage that he has an equation he can start with called the time-dependent Schrödinger equation, where we don't. We have to start from more fundamental principles. And the other thing, too, is that we don't, he has a sort of a hybrid ontology where you have a wave function and a trajectory, and we don't have that. We just have the trajectory ensemble itself. So it's very different from Bohmian mechanics, even though the trajectories themselves are more or less the same. So here's kind of a summary of the non-relativistic case. So these are three different viewpoints of what are mathematically equivalent things. You've got the Copenhagen interpretation, which says there's psi in the time-dependent Schrödinger equation, and that's basically it. In Bohmian mechanics, you have all of that, but in addition, you have a trajectory that obeys a Newton-type equation, where you add this extra quantum force contribution, which comes from a quantum potential, which in turn comes from an external field, the psi field, the wave function field. In our theory, you get this very interesting, well, it's interesting to compare this with this. So first of all, whoops. There we go again, okay. You get also a modified Newton equation, and that's it. It's a PDE now, though. It's not an ODE, because there are C derivatives that enter in. But the really interesting thing is that these C derivatives, which is this last complicated-looking term here, this is exactly equivalent to the quantum force, except that it's not generated from some outside field. It's generated completely intrinsically from the trajectories themselves, from the derivatives of the trajectories themselves. And the other really interesting thing about this is that there are only C derivatives in this quantum force term. So what that basically tells you is that all quantum effects in nature stem from interactions amongst nearby trajectories. Nearby in configuration space, not necessarily in position space. So you can derive this, as I said, from sort of deeper principles. It turns out that this is equivalent to the Schrödinger equation, and also these trajectories, each individual trajectory is equivalent to a Bohmian trajectory, although they come from a very, very different place. So these first 4 papers here kind of discuss the non-relativistic theory, which we've been developing over the last few years, and then this last one is the most recent, the relativistic generalization, which turned out, at least for me, to be very hard, but we think we're finally doing that right as well. So there are a lot of sort of broad-ranging ramifications of this kind of an approach. I'm really just going to focus on the theoretical/mathematical aspects. I just want to basically get the theory across in the 25 minutes or so that I get to speak on this. And even then, I'm going to have to make this very conceptual, given time constraints. I won't talk about computational numerical stuff at all, but of course, this is where the money comes from. And in terms of measurement interpretational, there's some really interesting aspects there. For example, taking a trajectory ensemble view of the double slit experiment is very interesting. But I'm not even going to talk about that. I will at least, though, say this much, which is that this theory kind of admits of a natural many worlds-like interpretation. The idea is you have, remember, this is a single particle theory, so every one of those trajectories corresponds to a different copy of my single particle. So you can think of each trajectory as being like a different world, all representing somehow quantum mechanically a single particle. But this is very different from sort of normal many worlds theory in 2 ways. First of all, the worlds talk to each other, which you definitely don't have in standard many worlds. And then the other big difference is you don't have this sort of infinite branching that happens. Space-time is foliated for all time, as it were, right from the start. So there's not this problem that anytime somebody measures anything anywhere, the universe branches into a million copies. That just doesn't enter in. But in other respects, conceptually, it's very many worlds-like. Okay, so one of the reasons why our trajectory approach is very sort of naturally suited to a relativistic generalization is because we're working with trajectories. We know that in classical relativity theory, you have an action, and you extremize that action, and the thing you're extremizing is your trajectory. Now, granted, the Klein-Gordon equation also can be derived from an action extremization, but it's a wave function that you're extremizing. It's a very different kind of beast, and so it's very difficult to compare. In our approach, though, you can very seamlessly and naturally go to the classical relativistic or even non-relativistic limit, just as easily as you can go to the non-relativistic quantum limit. All of these sort of limits pop out kind of naturally from this one unified trajectory-based framework. We also know, of course, that the Klein-Gordon equation has a number of problems associated with it, at least insofar as interpreting it as a single particle theory is concerned. Most of these have to do with the four-current density, which I don't have time to get into. There are also negative energy solutions, which also are something that have to be dealt with. Actually, you see that, of course, in the Dirac equation as well. All of these issues, though, they go away in our approach for reasons that will become a bit clearer later on. So this work can be said to be motivated by two questions. One sort of obvious question. We know that the Schrödinger equation is the most successful, one of the most successful physical theories, and we've heard a lot about that during this meeting. And we also know that relativity is right. Shouldn't there be some relativistic equation that the Schrödinger equation is the non-relativistic limit of? You know, and yeah, you can argue that, okay, that's what quantum field theory is, but shouldn't there be a way to do that for a single particle without having to invoke, you know, all of the extra machinery of second quantization? So that's one question. Another question, which is not so obvious, but is actually more important, is more of what I would call a kinematic question. Why is it that relativity theory provides no notion of global simultaneity for accelerating particles, although it does do so for inertial particles? So we're going to start with that kinematic discussion. And let me be clear, everything I'm talking about today is special relativity. These are flat Euclidean or flat Minkowski spacetimes that we're working on. although we're going to have accelerating particles. In quantum mechanics, this is known already in Bohmian mechanics. Even for free particle motion, you have accelerations due to quantum forces. So we have accelerated particles on flat spacetimes. And ultimately, we're actually going to work in curvilinear coordinate systems. So we're going to use a lot of the mathematical machinery of GR, okay, but our Ricci scalars are all 0, so this is technically speaking special relativity. If somebody at some point wants to throw in gravity, more power to you. I'm a chemist, but I think the foundation is there, but that's certainly not what we're doing or what we claim to do. So anyway, so the idea, if you have now, I'm talking about classical relativity theory, if you have a single inertially moving particle represented by this red world line here, even though the world line is local in terms of the space-time that it explores, it suffices to define a global inertial frame, right, represented what we call the primed frame, represented by these, the dashed lines. So the dashed lines then are the contours of T prime, and then the solid lines are the contours of X prime, only one of which corresponds to your actual world line, but any one of which could. And so you have, by following these dashed lines away from your world line, you have some concept of all of the events that take place simultaneously with this event on the world line. And so we call these things simultaneity submanifolds. Okay, and they're well defined if you have an inertially moving particle. But the problem is, as soon as you have an accelerating particle, even a mildly accelerating particle, you lose this notion altogether. So this is something that even in my student days always sort of bothered me, and I've never really seen a good explanation of this. Of course, the thing that people do in this context is they introduce what are called co-moving frames. So locally, of course, there's not a problem. We know that the points that that lie in the tangent space on vectors that are skew orthogonal to the velocity vectors, those are basically the local points of simultaneity. But then the problem, of course, is extrapolating outwards from your local trajectory, and the standard thing that's done is a sort of linear extrapolation. That would be your co-moving frame approach. And of course, the problem is that as soon as you accelerate, these things cross. And that causes all kinds of problems. So this point and that point are now simultaneous, which doesn't make much sense. And then, of course, on the far side of the crossing, you have a reversal of the correct time ordering. So there's a lot of issues associated with trying to define global simultaneity for accelerating particles. And in fact, all you can really do is define local simultaneity. There's no problem with that. But now look what happens when you introduce quantum mechanics. So now we have an ensemble of trajectories. You can define local simultaneity in little sort of local patches around each trajectory. And then you can just glue all the little patches together. And in that manner, you restore this idea of global simultaneity. So, and this, it looks simple in my cartoon. You have to kind of prove that it all works mathematically and work out what the conditions are, and that's, a bit involved. But it does actually all work. And so this is really this is the heart of everything I'm going to talk about today. This is the core idea that enables you to do everything else. And it only works because you're combining quantum mechanics and relativity. So the example I just showed you is what you might call the general. It's still, remember, a free particle case, although we could add an external vector potential field if we wanted. But you can still get quantum accelerated motion. In fact, that corresponds to the Gaussian wave packet, which I probably won't have time to talk about, so I'll mention that now. There's a special case that we call quantum inertial motion that corresponds to the quantum potential being 0 everywhere. If you have a quantum potential that's 0 everywhere, then the only solution, it turns out, are the solution of straight line parallel trajectories. And this is basically how you come up with the idea of an inertial frame. Okay, it's exactly like what I showed you before, except that instead of following one of these diagonal solid lines as your world line, we're following all of them simultaneously, okay, in the quantum picture. So this is, a sort of a way to think about what inertial frames really are. Okay, so that's a kind of a simple 1+1 space-time cartoon. Going forward, I want to get a little bit more mathematical and of course, move to a 3+1 space-time. So this is really just to establish notation. I want to emphasize also that there's the difference between two sets of coordinates. Remember, and this is where we really differ from Klein-Gordon and other field theories, our inertial x's, our inertial coordinates x alpha, these are the dependent variables, the things we're solving for. Okay, we now have to solve in the relativistic case for t as well as for x. Okay, of course, the description for Minkowski, flat Minkowski space in terms of these coordinates is straightforward, but in practice, those aren't the coordinates we work with. The coordinates we work with are the independent coordinates. And so these are what I call natural coordinates. So we have to find a way to define those. And so that's what I'm going to do now. So in terms of the space-like natural coordinates, the natural thing to do, the Lorentz invariant coordinates, are just these trajectory labeling parameters themselves. Just treat them like coordinates. So there are now 3 of them instead of 1. So these are the CIs. And we allow for arbitrary reparameterizations of those coordinates at this point. There's no reason to prefer one over another. But the trickiest coordinate here is the natural time coordinate and how that should be defined. So we're going to call this thing an ensemble time lambda. But again, now that we have the concept of global simultaneity, we have what we need to define our lambda coordinate. Namely, those dashed curves I showed you earlier should be the contours of the lambda coordinate, right? If they really do measure the progression of time in an ensemble sense, that is the proper way to define the ensemble time coordinate. So that's what we do, and beyond that, again, we allow for arbitrary reparameterizations. Later on, we're going to consider a very special choice of ensemble time, but for now, it's arbitrary. So this gives rise now to, this is a curvilinear coordinate system in general. It gives rise to a block diagonal metric tensor, so the spatial part we're going to call gamma, and then, of course, there's the G00. It's block diagonal because of the fact that the skew orthogonality is built in. But really, that's all that's built into this a priori. Okay. It's natural to ask, now that we've defined this ensemble time coordinate or family of coordinates, is it possible to interpret the normal proper time, which now, by the way, is a bona fide coordinate over all of space-time because there's one trajectory at every point in space-time. Is it possible to interpret this thing as an ensemble time? And the answer is no, it isn't in general. But we shouldn't be bothered by that. Here's the general relationship between the two, by the way. It's just G00 itself. But this, in fact, it gives rise to what we call the generalized twin paradox, which, if you know the normal twin paradox, really is no paradox at all. So here's the regular twin paradox. So in normal relativity, we don't have global simultaneity, so we can only talk about simultaneous events when 2 world lines cross. So here's an unaccelerated and an accelerated observer, and they cross at some initial time, and they cross again at a later time. And of course, these events are simultaneous, these events are simultaneous, but the passage of proper time is different for these 2 trajectories. The one on the left, of course, ages more than the one on the right. In our relativistic quantum theory, we have what we call the generalized quantum twin paradox. So this is different because we don't have 2 observers, we just have the one, but we have multiple copies of that observer. And of course, the trajectories never cross, but they don't have to because we now have global simultaneity. So we can say that these 2 events happen at the same ensemble time, these 2 events happen at the same ensemble time. But of course, the passage of proper time is different because this one is not accelerating and this one is. Now, you might be inclined to think that in this particular example that the guy on the left actually ages more. That turns out not to necessarily be true for a reason that I'll explain in a moment. But for sure, there's a different amount of proper time associated with both of those trajectories in the ensemble. Okay, so now from the set of all possible ensemble times, I'm going to pick out one special one that we call ensemble proper time. And what this is this is the one that reduces to the normal proper time for a quantum inertial motion. Okay, so in the case of quantum inertial motion, you can show in that special case that tau is an ensemble time. Okay, so and then from that you can generalize to get something we call the ensemble proper time, capital tau. And here's the definition of it, and you can see that it reduces to the normal proper time when q is equal to 0. Okay. But the other very interesting thing about this relationship here, it says that q itself plays a dynamical role with respect to the progression of time, and moreover, that this role depends on the absolute value of q, not on its gradient, right? So normally we have a potential in physics. It's not the absolute potential that matters. It's only the gradient that matters, or the potential differences. But here we have a case where it's actually the quantum potential, the value of the quantum potential itself that plays plays this role. And of course, this is very reminiscent of the gravitational potential. In fact, you can make this comparison here, compute G00 in the weak field limit, and you see that you get very tight correspondence between Q and the gravitational potential. There's a sign change overall, which we don't quite understand, but that doesn't matter so much. The really important thing here is that the quantum potential, and those of you who are Bohm people know this, it can be either positive or negative. So what this basically tells you is that in relativistic quantum mechanics, you can have either time dilation or time compression. And in fact, you can show that time compression, which of course doesn't happen classically, this corresponds to the tunneling regions, or the classically forbidden regions of space, which is a kind of interesting thing to come out of all of this. So, all right, so at this point, we're kind of spilling into dynamics. How much time do I have? 9 minutes, okay. Well, and so the dynamical part is actually the part that requires the most mathematics and is the hardest part of the derivation, but it's less conceptual, so I'll spend a bit less time discussing the dynamics. But to go from what I've just described, which is basically just a kinematic picture of trajectories in space-time, to an actual dynamical law, proceeds through a series of stages. So the first thing that we're going to need, and we need the same thing in regular Bohmian mechanics, we need some kind of probabilistic structure on top of the trajectory structure. And in particular, in Bohmian mechanics, it's well known that probability, not probability density, but probability is conserved along trajectories. So we want to basically take that condition and translate it over into our relativistic picture. That turns out to be involved. I think it was Ed Nelson who said the other day that probability and relativity don't always match very well. So there are some subtleties here, but we think we've finally sort of worked out the right way to do this. And basically, yes, we want to take this notion of probability conservation and apply it correctly in the relativistic, or at least curvilinear framework. And so we have basically a spatial probability density we call f of c that lives essentially on c space because it's conserved along individual trajectories. So there's no time dependence to this thing. And then, of course, you can take this thing and you can do all your conversions over to inertial frames or whatever you want to do. But this is something that needs to be added on top of the theory that we already have. Then, of course, we don't have a Schrödinger equation from which to work. We're going to derive our dynamical law the right way from a Lagrangian. So then you have to worry about what the Lagrangian should look like and so forth. And there's pages and pages in that last paper that I wrote that kind of justify the right approach to use here. Actually, some of this, just as an aside, even in the non-relativistic case, since even there we're not starting from the time-dependent Schrödinger equation, you have to be very careful about what assumptions you make that give rise to the right dynamical equations. But all of those assumptions do carry over into the relativistic case. And at the end of the day, what we wind up with is an action that's a sum of two parts. There's the usual relativistic, the usual relativistic classical action, and then there's a quantum action, which essentially comes from a quantum Lagrangian, which is just minus the quantum potential. Okay, so if you were to just do the natural thing, write down exactly the form of the Lagrangian that you would think that you would need in this context, it turns out to be the right thing to do, but you have to go through quite a bit of work to show that that's the case. So this gives rise, okay, so then the final thing we have to do is actually define the quantum potential itself in the relativistic context. And so there it is. I'm not going to spend any time talking about where we got this. I will point out one thing, though. Notice that it depends on the spatial part of the metric tensor only. Spatial meaning C now, natural coordinates, not inertial coordinates. It does not depend on tau or lambda. It does not depend on the ensemble time. That's very, very important. What this is going to mean, essentially, is that we wind up with force vectors, quantum force vectors, that live on the simultaneity submanifolds. And if they didn't, then the present forces would be referring to future or past times, which we regard as a bit of a causality paradox, and in fact is something that you see in no other viable theory of physics that I'm aware of anyway. So there's an asymmetry with respect to how we treat natural coordinate space and natural coordinate time. However, at the end of the day, well, you can already kind of tell from this equation, but you can tell a little bit better from this equation, which is the Euler-Lagrange equation that we get from extremizing the action for this trajectory ensemble. So this basically tells you this is exactly what we want. These are the PDEs for the x alphas, for the inertial coordinates, in terms of these natural coordinates. Yeah, okay. And we see basically that, indeed the inertial coordinates are treated symmetrically, but the natural coordinates are not. In fact, this PDE is fourth order in space in C and second order in tau, which corresponds, by the way, exactly to the non-relativistic limit of this theory. It also has a different order in space and time. But from the point of view of inertial space and time, things are treated on an equal footing. Okay, so this, of course, we all know where the Dirac equation came from in this problem of making the order in space and time the same, whereas in the non-relativistic case, they're different. Well, this is, at least we regard this as kind of a resolution of that problem. And if you included a natural time component to your quantum force, then of course everything would be the same order. It would be fourth order in both, but it would be wrong, basically. You would have these problems that arise from this causality paradox. The very interesting thing, if you do that wrong thing and you add that extra component that should not be there, you can show that the resultant equation is mathematically equivalent to Klein-Gordon. Okay, so there are two things that pop out of this. First of all, this tells us that what we're doing is different from Klein-Gordon, and exactly how it differs from Klein-Gordon. The other thing that it does is it shows us essentially why Klein-Gordon goes wrong, where all of these sort of well-known problems come from. And in fact, in our theory, we don't have those problems. All the trajectories are sub-luminal and so forth. And we also don't have negative energy solutions. And there is actually one case where Klein-Gordon matches what we have exactly, which is the plane wave solutions of the Klein-Gordon equation. Those are exactly what we call quantum inertial motion. So in that case, you can kind of compare directly. But more generally, you can. And also, I should mention, our theory is inherently nonlinear, so there's no superposition principle either. Okay. So then you can go on and do the usual thing, apply Noether's theorem and derive your energy momentum tensors and conservation laws and so forth. There's actually two completely different sets of conservation laws, though. One that has to do with inertial coordinates, and the other, which is the sort of the familiar one, and the other one that has to do with the natural coordinate system, which, so far as I know, doesn't have an analog in other areas of physics, or at least not that I'm aware of, but is nevertheless interesting mathematically. We've also done some Gaussian wave packet propagations, but I think in the interest of time, I will not talk about that. Including questions, though, right? Not including questions? Okay. Well, let's talk about Gaussian wave packets. So, being a chemist, I have to do calculations to justify my grants and so forth. And so in 1+1 spacetime, you can actually propagate the Gaussian wave packet for different values of the speed of light. And you get kind of the behavior that you expect to some extent. So for example, if the speed of light is very large, you see that everyone agrees that the time contours are basically horizontal lines or close to it. But of course, in the ultra-relativistic limit, you get much more distorted simultaneity submanifolds and so forth. We had hoped to get an analytic solution for this, but that's not possible because a Gaussian wave packet preserves its shape non-relativistically, but that also means that the velocities on the fringes get arbitrarily large, which we obviously can't have in a relativistic theory. So far we've not come up with a relativistic generalization of the Gaussian wave packet from the point of view of an analytical solution, but we do have these numerical solutions. And there's some really interesting dynamical things going on here, but I think in the interest of time, I will, again, only talk about those if somebody asks me a question. And we'll move on to the obligatory acknowledgement slide. Thank you.